Okay, Assalamualaikum warahmatullahi wabarakatuh and good evening. Okay, so now we are in chapter 4. So we have finished chapter 3. So in this chapter 4, so we will discuss on a Fourier transform. Okay, so let's start. First, we need to understand or we need to know a definition of Fourier transform. So Fourier transform is a method for representing signal and system response in frequency domain. So this means if you have a signal or system response in time domain, so you can transform it into a frequency domain using Fourier transform. So this means Fourier transform is just a tool or method that we can use to transform our signal or any signal in time domain into a frequency domain. Okay, Fourier transform is an extension of Fourier series, okay, which is extension the concept of Fourier series, where in Fourier series, okay, we just consider a periodic signal. Okay, however, okay, for Fourier transform, okay, so we extend concept of Fourier series so that in Fourier transform we can have a periodic signal and also a non-periodic signal. Okay, so that is Fourier transform. Okay, so let's take a look how we extend concept in Fourier series into a Fourier transform. So if you look over here, so we have a signal xt. This xt is a periodic signal, okay, where we have represented in a complex exponential form, okay, which is summation of Cn e jn omega naught t, where n start from n equal to negative infinity until n equal to plus infinity, where your Cn, okay, where your Cn is Fourier series coefficient, where we can calculate that using this equation, which is 1 over t naught, okay, and then integration over one period xt multiplied with e exponential e power of negative jn omega naught t and dt. If you can still remember, if you want to draw frequency spectrum of our periodic signal, okay, for this case we have complex exponential form, so we will draw magnitude spectrum and also phase spectrum, okay, where both frequency spectrum graph, we need, if you want to draw it, we need to refer to our Fourier series coefficient Cn, where our Cn is a complex number. So to draw magnitude spectrum, so we will calculate the magnitude of Cn, and then to draw our phase spectrum, we need to calculate our phase of our Cn. So to draw both graph, okay, of our frequency spectrum, it must refer to our Fourier series coefficient of Cn in complex exponential Fourier series. Okay, so if we have over here, okay, so you have Cn, okay, which is we draw this one, which is referring to x omega, which is this one referring to the magnitude of our x omega, okay, where our xt is our periodic signal, okay, with t naught over here, with t naught, which is the periodicity of our periodic signal xt. Okay, so how we want to extend Fourier series concept into a Fourier transform. Okay, so as in Fourier series, we just consider xt as a periodic signal. Okay, in order to consider a periodic signal, you can imagine if we can extend our t naught further, or we increase our value of t naught. Okay, so for example, we move this much further away. okay, or further apart. So we increase the t naught over here. So by doing that, okay, so we have increase in t naught, but we decrease in our omega naught. Since omega naught is equal to 2 pi over t naught, increase in t naught will cause our omega naught reduce, okay, in terms of the value. So if you look over here, since our omega naught reduce, so that means our magnitude graph will be much closer to each other when compared to this one. Okay, alright. So because this one T naught is smaller than this one, okay, so in terms of the frequency, so this one is much larger in terms of the frequency when compared to this one. So this frequency much smaller compared to this one. Okay, as we increase further the T naught, meaning that these two part over here is getting further away. Okay, so the T naught is increased, and then omega naught will be smaller, and then the graph, okay, for our Cn is much closer to each other. Okay, so if we increase this, okay, T naught into infinity, so that means this part will go to positive infinity, and then this part will go to negative infinity. So we only have this part remaining at the center. Okay, so meaning that this is a periodic signal. Okay, a non-periodic signal. Okay, which is a rectangular shape signal. Okay, okay, this is a non-periodic signal. Okay. Okay, so this is a non-periodic signal. So we just have a rectangular shape of signal for this one. So because this one is very further apart, okay, which is this one located at positive infinity, and then this one located at negative infinity. So we have remaining a rectangular signal, okay, which is a non-periodic signal. Okay, by doing that, okay, T naught is equal to infinity, then T naught will become very small, and then this one will be equal to delta omega. Okay, since it's very close to each other, okay, so we can say that, okay, for this signal over here, okay, which is where we extend T naught into equal to infinity, so we have a non-periodic signal, and then our x omega, which is equal to the magnitude of our Cn. Okay, as x omega, okay, is equal to Cn, which is we refer to the magnitude. Okay, so meaning that this one is the magnitude of Cn. Okay, which is we refer to this one is magnitude of x omega in frequency domain. Okay, so this one over here, so meaning that, okay, so we have Cn equal to 1 over T naught, and then integration over 1 period xt multiplied with e negative j and omega naught dt, and then we say that this one Cn is equal to x omega, and then the limit now change, okay, because we because of the value of T naught is equal to infinity, so the limit of the integration now change to negative infinity to infinity, okay, plus infinity, and then xt multiplied with ej omega t dt, where n omega naught t now need to be changed to omega. So this is what we call a definition of Fourier transform, where over here x omega is a frequency in frequency domain, which is a representation of xt in a frequency domain, and then xt now over here is in time domain. So that means we can use definition of Fourier transform, okay, to transform time domain, okay, signal in time domain into a frequency domain. So if you look over here, so we have what we call Fourier transform of operator, which is f over here. So this is f, meaning that we can write it down like f, and then we put bracket xt. Okay, this means that this f Fourier transform operator means that we want to have Fourier transform of xt. Okay, so this means that Fourier transform of xt will be equal to x omega, and then this one will be equal to negative infinity to positive infinity xt e negative j omega t dt. As we know, x omega is a complex function, same as our Fourier series coefficient of Cn. So we can draw in terms of the magnitude spectrum and also phase spectrum. But in general, so we consider or we call x omega in terms magnitude. The magnitude we call it as amplitude spectrum. Okay, while in phase, okay, we call it phase spectrum. Okay, so hopefully you understand what is the definition of Fourier transform. Okay, which is a tool or method to represent our signal in time domain into a frequency domain. And then Fourier transform is just an extension or concept of Fourier series, where now we cover both a periodic signal and also a non-periodic signal. Okay, so hopefully you can understand. Okay, later, okay, in the next video, we will discuss on how you want to transform any signal, okay, in time domain into a frequency domain using definition of Fourier transform, okay, which is this equation. Okay, so see you again in the next video. Okay, thank you for watching, and then bye.